In this video, I wanted to talk about one of the more visible applications of diodes, and that is light-emitting diodes, or as we know them more commonly, LEDs. So in circuits, LEDs behave very similar to diodes. Their symbol is almost the same as a diode. They're sometimes, they're drawn with little arrows pointing away from them most commonly. Sometimes they're in circles also, but usually there's some arrows pointing away from them indicating that there is light being emitted. And light-emitting diodes are still going to allow current through in one direction and basically not allow current in the other direction. Light-emitting diodes are not going to like reverse breakdown, so we don't have Zener light-emitting diodes. But we do have current allowed to flow through them this way. In general, current not allowed to flow through them that way. And that means for an LED to work, we want this end to be at a higher voltage than that end. Now for silicon diodes, that is not LED, the forward drop that we get when we have current flowing through the diode, and again, in our real model, of course, this depends on how much current we're flowing, but our simple model of the silicon diode is the forward drop is approximately 0.7 volts. This particular value has to do with the fact that this diode is made of silicon, and silicon has a particular band gap. That is, there's some energy difference between electrons in what we call the valence band and the conduction band, and you have to apply enough voltage to give them enough potential energy to get them to want to jump from this one kind of silicon to this other kind of silicon, the P and the N that we were talking about last time. So this 0.7 volts is a consequence of the fact that these diodes are made of silicon. Okay, LEDs are not made of silicon, and the reason for that is the band gap of the material needs to be bigger in order to have the electrons as they jump from one side to the other to emit light that's in the visible range. So silicon diodes, it turns out, this energy is small enough that it can emit light in the far infrared that we can't see or really use. But if we make a material with a larger band gap, you can make the light big enough to be visible. Now this is a big thing in solid state physics or materials science or materials engineering. Lots of people spend a lot of time wondering about band gaps, so this is a big deal in science and engineering. So it turns out for red LEDs, which are I think still probably the most common, we get forward drops. Well, first I should say red LEDs are made of compounds like gallium arsenide or gallium aluminum arsenide or gallium phosphide. There are all these different binary or trinary semiconductor compounds, so made of a few different elements, not just pure silicon with a few atoms added to it. So anyway, as a result of that material choice, red LEDs have a forward drop of roughly 2 volts, or like 1.9 volts. We'll just say 2 volts. And this is 2 plus or minus a couple tenths of a volt, right? Yellow and green LEDs are also made of similar materials with similar band gaps. The yellow and greens tend to be slightly higher, but very generally, yellow and green might be around like 2.2 volts or something like that. And your numbers for these might vary by a couple tenths of a volt. Blue LEDs, which were really only developed within the last 20 years. Red LEDs have been around for 50 or more years. Blue LEDs really only around 20 years, and actually the inventor of how to grow the materials, the semiconductor materials to make blue LEDs, the most common is gallium nitride, I think. He won a Nobel Prize a few years ago for figuring out how to do that growth. Anyway, so blue LEDs, the blue light has more energy, shorter wavelength, higher frequency, etc., more energy than the other ones, and so it needs a larger band gap and a larger voltage. So blue LEDs are going to have a forward drop of roughly 3 volts, maybe we'll say 3.2 volts or something like that. Very, very roughly 3 volts. And so these are most of the colored LEDs we encounter. We also can have LEDs that emit ultraviolet light, and in the process they may emit some light you can see, but they're emitting a lot of ultraviolet light you cannot see. Those might have a band gap of roughly 4 volts or somewhere in the high 3s. So ultraviolet LEDs are kind of rare. I have an ultraviolet flashlight that uses ultraviolet LEDs that I got somewhere. We also can have light with less energy than the red, that is infrared. So you can buy infrared LEDs that emit light that you cannot see also, but is a longer wavelength with less energy than red light. And these are going to have a band gap of less than 2 volts, maybe 1.7 volts is what I have on this source. So infrared LEDs are actually really common. That's what we use in remote controls. The remote control, when you press a button, it blinks a little infrared LED, and there's some sensor on your TV that can see that infrared light that we can't see with our eyes and turns that into an electrical signal and so on. So yeah, these are all the different LEDs we may encounter. In our labs, we're going to be using mostly red and green and blue, and we can make measurements of these forward drops. As a quick word of warning, though, remember that these curves are still exponential. So this turn on might happen at 3 volts or something. We'll just say for a blue LED, 3.2 volts. But we still need to take care with LEDs in circuits. And what I mean by that is if we just connect a blue LED to a 5 volt voltage source directly, like something like this. That's our LED with light coming out of it. If we try to do something like this with 5 volt source, 5 volts is somewhere over here. So how much current do we get at 5 volts? It's going to be a lot of current. So we never want to do something like connect an LED directly to a voltage source because of this exponential behavior. You might say, oh, well, what if I have it exactly at 3.2 volts? Would that be okay? Yes, but if there's any variation in that, you're going to change the amount of current flowing by a very large amount, and so that's considered bad practice. The better thing to do is to, I shouldn't delete those, this is still an LED. The better thing to do is to put a resistor in series with your LED, and you can pick the value of this resistor so that you flow the right amount of current through your LED. So normal LED currents are something you should look up from the LED manufacturer, but very generally for normal LEDs, the kinds we're going to be using in lab that are 5 millimeters wide or something like that, those might need 10 milliamps of current or 20 milliamps of current. If you try to push more than that, you will probably burn them out. You certainly can buy LEDs with higher currents, but anyway. So you want to pick this resistor value so that given the forward drop of your LED, this resistor is causing there to be 10 or 20 milliamps flowing through your diode. So we'll do some examples of that calculation later on, but this is a practical and important lesson about LEDs because everybody wants to use LEDs in a project because they light up and they're awesome. But I will just write need resistor in series with your LED, and I'll put exclamation points after it so you know that I'm being serious.